I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you to guide our thoughts today, Lord. In your name I pray. Amen. Let's see here. You guys have any questions about anything in particular before I get started? So let me just talk to you. So I'm going to talk to you about some theorems that we know for groups of units. So we've been using the notation Zn star, right? So what was Zn star? The group of units, right? In Zn. Now, another popular notation for this is Un. So this notation is from Galeon's Abstract Algebra, among other places. It's the book I used last year. Well, it's not actually Abstract Algebra. It's Contemporary Modern Algebra or something. I forget. Anyway, but Galeon's text. And so, let's see here. What's the order? What's the order of Un? Right. This is exactly N. It's the number of relatively prime right? K to 10 in Zn, of course. Now, and so I guess we have developed, I mean, I've said some things about this in various homework exercises here and there, right? But I don't know if we ever really quite just talked it out. So let's just make sure we have, for future reference, a few things settled. One of the first propositions that we can easily establish is that if we take the Euler phi function of a prime, right, this should be equal to what? Yeah, p minus 1 for p prime, right? And sort of a corollary to that is what? The cardinality, the size of the group of units for a prime is just what? Just, I mean, every once in a while I'll throw that back in there just to remind you. But this is p minus 1, right? Let's see here. What else can we say? What if you look at the group of units to a prime power? If we look at phi, or sorry, I'll state it in terms of Euler phi function, but what's the Euler phi function of p to the k? Where k is greater than or equal to, I guess we should probably say 2 to keep it interesting, right? We already got, I mean, maybe this is, we can decide when I write this formula down. You just told me, Sam, what was it? P times p minus 1? I think it's p to the k minus p to the k minus 1. So let's see, does that, if I plug in k equals 1, does that make sense? Yeah, k equals 1, it reproduces this, right? K equals 1, I get p minus p to the 0, which is p minus 1, which, so no need for that. We can throw 1 into the mix. And so basically, the proof of this, we should think about, you know, the group of units. Well, let's just say we should think about Zn, Zpk, right? So we want to find the numbers in here which are relatively prime to what? P to the k. So if you start listing them, 1, 2, p, right? If well, say p minus 1, p, then what comes next? P times that list, right? What's that? Except what? Oh, yeah, I'm going to throw that out. I'm just trying to list them all. I'm sorry. Maybe I'm doing the wrong thing. Maybe I should try to list the ones that are divisors. Maybe that would be more productive, huh? Is that more? That might be more productive. I mean, this list I'm writing right now is not particularly interesting, right? 2p minus 1, 2p. This goes on for a while. Eventually, we get to p to the k minus 1, right? And then I guess if you're going to throw 0 into this end, you can put it over here. Anyway, there's p to the k worth things here. Maybe it's more productive to list the factors. What are the factors? Let's do that. This is just all the numbers. So we need to throw out this one. Obviously, we need to throw out that one, right? Can anything in here be a divisor of p to the k? Think about it, it can't. Could anything in here be a divisor of p to the k? Yeah, I can kind of see that intuitively. So it's not quite a proof, is it? What are the divisors of p to the k? Maybe that's a little bit easier to actually list, right? You got 1. You've got p. You got what else? Of course, p squared, and so forth. P to the k minus 1. But what else is there? But are multiples of those, can a multiple, if I throw in another prime, right? If I say q times one of these guys, can that divide p to the k? No, it can't, right? Right.
Divide PQ. I mean, 2b is not relative prime to b to the k.
I'm sorry, 2p, what are you saying?
2b is also not relative prime to the p to the k.
Oh yeah, I shouldn't, you're right. I have a problem. I shouldn't even throw out that, should I? Unless p equals 2. So my initial thinking was wrong, wasn't it? Yeah. I mean, p is right. That's got to be thrown out, obviously. But these are the divisors of p to the k, right?
Not necessarily, because like if k is 5, like say k equals 5, p squared doesn't divide. Wait, yes it does. That's what I'm saying.
How many of these are there? See, I see, I mean, I can see getting rid of,
Oh, you can get rid of, there's k of them.
there's just k of these.
No, you cannot get rid of one. One is relative prime to anything.
Ah, curses.
Right, you get rid of 0 instead. Okay.
How do we get to p to the k minus 1 though, huh? I mean, apparently we have to remove that many of them. Let's look at an example. Maybe that'll be helpful, right? Let's look at 5 squared, right? What are your numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I really committed to this, didn't I? 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25. Ready or not? Here I come. Let's see here. Oh, I already got that one. Sorry. I just made the board into a cylinder. Oops. But a little topology humor for you there. So we got to throw out this one. We got to throw out this one. Got to throw out this one, I think. Or do we? Oh, relatively prime. Not Not divide. My condition's too strong. You guys, I got to. I'm putting it back in there. I'm putting it back in. See the GCD. You guys talk me. I mean, I talk myself out of it, I guess. The GCD of this and this, it's not 1. It's p. Assuming p is not equal to 2. So those are not relatively prime.
Well, the divisors are very helpful then because you just have p minus 1 of each of them. That's all the multiples of each of those. So for like p, you have 1p, 2p, 3p, all the way up to p minus 1 times p.
So you're saying these divisors, and then there are p minus 1 multiples of these? Do we agree with him?
Because that's double counting or multiple counting a lot of things.
So we got 5. 5 produces what? 10, 15, 20. And are we going to throw 0 in there? I don't know. I mean, if setting 0 aside, you know, looking for non-zero multiples, because 0 is going to be in everything. We don't want to count that, do we? I mean, you can count it, but then you got to uncount it. Count on that. Sorry. So guys, help me out. I'm not good at counting. This has been established. So you're saying 5 times 4 gives me what? And that would be 5 squared minus 5, yeah. All right, so how do we count? You have these are divisors, so those are definitely out. But then multiples of divisors share p, or a higher power of p is a GCD with p to the k, right? So those are out of the units. The question is, how many of those are there? So this, I've got how many of these? It's a bad way. I have those k minus 2 of those, right? And each one of those, I have p minus 1, right? P minus 1 multiples of each, is that what you're saying?
Because every multiple of those higher powers is also
Ah.
so you really can get away with just counting multiples of p.
So it suffices to count multiples of p, huh?
Yes.
How many of those are there? Nah.
Yeah, well, you can show that any natural number times p divides p to the k. It's not just 5.
Or it's not relatively prime.
Right. It shares p as it divides.
If m does,
The greatest common denominator is greater than or equal to p. Right.
or, I mean, m does not share p's.
But there are p to the k over p of them. Just the GCD is greater than or equal to p, not necessarily equal to p. And therefore it's not less.
Say again?
The greatest common denominator, if m is the power of p, the greatest common denominator would not be equal to p. But it's going to be greater than or equal to p in any case, because p is a factor greater than it.
Right.
That is always
P is a common factor there, so
right.
so how many choices?
But yeah, there's p.
So how many MPs are there?
P to the k over p, which is p to the k minus 1. Right.
You guys got to slow down. So how many of these are there? There's what?
P to the k over p, which is p to the k minus 1.
How do you know P to the K over P?
Because that's, if you take a divisor of p to the, if you take a divisor of p to the k, then the number of
They're all
space
spaced out
because it's
exactly by p distance.
yes, and if you divide
Uh-huh. 25 over 5 gives me how far they're spaced.
So that's how many of them are not relatively prime. So then we subtract that from p to the k, and that's what we have.
These are not this many not relatively prime. This many non-units. Is that all of them?
Yes. By, I mean, that's what the proposition says. But yes, it's also.
So that's true, it's just convincing ourselves of that. Because everything is a multiple of p.
Like MP is less than b to the k, right? So there's zero m is from 0 to b to the k minus 1 minus 1. Then b to the k minus 1.
Give me the inequality M satisfies again, King. MP is less than
Less than, not
p to the k.
and greater than or equal to 0. So m is between 0 to b to the k minus 1 is equal to.
Yeah,
You
you
have
got it. Divide by k.
And then what? What?
Divide by p, and that gives you m is greater than or equal to 0, less than strictly.
Oh, I'm sorry. I see what you guys are saying. Divide this inequality. I gotcha.
Yeah, there. And each m represents a unique multiple of p,
Yeah.
which gives you p to the k plus 1.
You guys said if you believe this, if you guys understand this counting, then that follows immediately, right? So, because I have p to the k total things, and then if those are the non-units, then everything else left is a unit, right? That includes 0 and the multiples. So, all right. Anyway, now that everyone's thoroughly confused, feel like I did my job. Woohoo! So let me go on. Not so sure about that. I mean,
I think you can since p is so I think it's actually really easy.
oh, it's easy induction?
Yeah.
Ah.
See, I thought it was like b of p to the k.
So what would the inductive argument be?
Well, assuming we already have to.
It's k equals 1. We already did over here.
Yeah.
We should fix, now, induction on what? K or K, right? Yeah. Fix P. Let's say fix P prime, right? Obviously. So you want to assume it's true for what? For K? All right.
So then show that for p of p to the k plus 1, that equals p to the k plus 1 minus p to the k.
Ah. And so, I mean, I don't not believe you, but how do you show it?
So phi of p to the k plus 1 is the same as phi of p to the k times p, and then use homomorphic property to say that it's equal to
Oh, so you're using that phi of,
times phi of p.
no, wait a minute, hold on a second here. Phi of p to the k plus 1, you said is equal to phi of p times p to the k
Yeah.
times p.
Uh-huh. And then since it's homomorphism, that's equal to phi of p to the k times phi of p.
Did we know that phi is multiplicative?
Well, whatever it is,
But the thing is, see, the next theorem I have to prove is this. If we have u of st, it's isomorphic to us cross ut, but there's fine print on this subject condition. What's the condition? Yeah. So I'm not, are you sure about that? Because I don't, these are very much not relatively prime. I mean, So I don't know if I can.
That's why I'm talking.
I can't make the step that you want to make. I can't. It's not multiplicative for, like, okay, for example, you know the Euler phi function of 4 is what? What are the things relatively prime to 4? 1 and 3. All right. So phi of 2. Phi of 2. What's that? So
Couldn't you just on the other side say plus? No. You couldn't say that.
I mean, this shows that phi of 4 is not.
Right. With respect to multiplication. Okay.
But that's what
Oh, is it supposed to be additive?
no. You're right. It is multiplicative only.
I thought the Euler phi function was a multiplicative function, but not.
Right.
Only when you have relative to prime.
See here, at the level of the Euler phi function, this statement is that, see the Euler phi function, or Euler's Totient function, st, and what's the size of this? What's the size of a Cartesian product? It's the product of the sizes of the things being Cartesian. That's not a word. But this is phi of s times phi of t, right? So I have this multiplicative property for the Euler phi function for relatively prime things. Dang it. I wanted to believe you. I wanted it to work, Alan. I really did, because I am miserable at that counting, but the argument I've seen in books is that counting argument. So it's okay. I mean, it always makes me happy when we can actually relegate things to just that. Okay, let me get out my my projector here. If I can find my laser. So some of these things I'm sharing with you guys today, they'll be really helpful for you working specific problems as we go on, you know, because there's questions which involve this technology, and it's kind of gotten suppressed in some sense by our book and by just the way things have gone this semester. I mean, just the natural ordering of the book I used last year, it just leads you to the question, what do the group of units look like, you know? How can you decompose it? And these questions, they just kind of naturally pop out at you. The structure of our book is a little bit different. It led to a different discussion, and that's why we haven't said some of these things in class yet. But we should, because they're kind of nice, easy things to know and use and play with. So here's the proof that this is the direct product. Now that was you should replace that with equals. Yeah, sorry about that. So basically the isomorphism is that you go from the ST congruence class to the S comma T congruence class. This is the isomorphism actually between this and that. And so this basically just shows that. I mean, if I have YST, I get YS comma YT, and if I add J copies of ST, right, this would be what? So here's a representative in UST. What would another representative of the same coset look like? The same residue in ST. It would look like J times ST, right? So this would be another representative for Y, X plus, I'm sorry, I've lost track of what this is where the relation was up here. I can't read my own notes. See? So X and Y are different representatives of the same residue in mod ST, the mod ST world. Modesty. Modest is the hottest. Sorry, I see here. I can't help myself. Who put that up? Like, did that? I can't believe that was actually. Anyway, I mean, I never went to the gym, you know that, but I heard from other professors who did. The modest is hottest campaign. Seems there's so much wrong with it. I don't even know where to start on that one. But anyway, getting back to this. So this is a multiple of S. That is a multiple of T. So where does it go? Into the S and T congruence classes, right? Which shows you that this mapping is well defined. And then you need to show that it's a homomorphism, I think. Let's see, what did I do? What did I do next? Oh, I actually found the inverse to it? Okay, well, that'll show it's a bijection, I suppose. And then I calculate the why did I calculate the kernel? If I already noticed the inverse, shouldn't that just be 1? That better just be 1, right? Otherwise, the inverse I found is rather surprising. If you find a non-zero kernel for a bijective map, you should be worried. Non-identity kernel. But anyway, I guess I'm just studying what it is that's in the kernel. It's x, st is in the kernel if and only if x is congruent to 1 and x is congruent to 1 in mod s and in mod t for s and t relatively prime. My point was that the Chinese remainder theorem says that there's a simultaneous solution to these congruences, and it is 1 mod st. So anyway, let me not belabor the details here. So of course, the immediate corollary to that is that if we have relatively prime numbers, then the Euler phi function of st is phi s phi t. And there's also an extended Chinese remainder theorem. If I have this system of congruences, all right, and they're subject to relatively prime moduli, this is unfortunate. What are these supposed to be? Those are m's, right? Otherwise, there's no n's anywhere else, right? So if you have a set of relatively prime moduli, then there is a unique solution to this system of congruences. And, well, it's unique, not really. It's unique up to the product of the moduli. So it's not really unique, right? Yeah. So the proof is actually quite beautiful. You can construct this solution as follows. What you do is you take m sub k to be m over mk, and that means that if you look at that, see what I've done is the big M is formed by the product of all the relatively prime moduli, right? So if you take that and you divide by m sub k, you've removed the m sub k factor from it. So when you look at the GCD of this and that, there's no m sub k common to both. There's no common factor, so this GCD is 1. It's very sneaky. So by construction, all the factors composing mk are relatively prime. Yeah. So for each k, by Bazou's theorem, we have that the greatest common divisor of that is 1, which means that we get the y sub k and b sub k such that this sum to 1, right? Which means that yk mk is congruent to 1 mod mk. And you can find these inverses for mk mod mk for each k. And so then, by math magic, you consider the weighted sum of these guys. So these are built from the inverses, which I just explained the existence of, and the a's, where are those coming from? That's from the original system. And it turns out if you just do a times this plus a2 times that a2 times this plus that ar times that, that's actually the solution. And it's easy enough to see that because if you look at this and you consider it mod mi, what happens? Well, the mj's are 0 except for, except for j equals to I. So that makes all of this just truncate down to x, ai, mi, yi, and that's going to be congruent to, why do these cancel? By construction, y was the inverse of mi, mod mi. So that's just ai again, and there you go. But I being arbitrary, that shows you that it solves all the congruences at once. And then if you look at another solution, then you can show that their difference is congruent to 0 mod the product of the moduli. So this is the extended Chinese remainder theorem. Although there are worse versions of this. There's some kind of version of the Chinese remainder theorem for when the moduli are not relatively prime. There are things which are known about when There's some sort of interlinking between the moduli. If it's more complicated, I don't know it. Here's a nice simple example of Chinese remaindering. If I want to solve x equals 2 mod 3 and x equals 7 mod 11, I construct my m, the product of all the moduli, which is 33. So if I remove the first modulus, I get 3. Wait a minute. I guess my m1 is I divided by 11. And, oh, I'm sorry. I can't read my own writing. So my first moduli is 3. I divide by 3, I get 11. My second moduli is 11. I divide by 11, I get 3. So if we look at the 11, let's see here. So 11 inverse is equal to 2. That's my y1. That's my y2. I build it together. I get x is equal to this times, building it together as I just described, we get 128, which is 29 mod 33. And you can check that 29 is in fact congruent to 2 mod 3 and congruent to 7 mod 11. So I know I'm going through this kind of fast, but it's a well-known technique. If you got to solve a system of congruences, this is how you can do it. Of course, the other way you can do it is just to sort of like substitute the ambiguity of one equation into the other and just work out what's possible. But this is kind of a nice method, right? Although the substitution method will even treat the case that the moduli are not relatively prime. So the meaning of that, basically the import of that is that we get this isomorphism between the group of units of, the product of a bunch of relatively prime moduli is just this, is isomorphic to this direct product of units. And essentially it's the same argument as we just gave for 2. It's just that you have psi x equal to, psi of, last time we had like st, now we've got m is m1 through mr. And you just pick off the m1 residue, the m2 residue, the mr residue, and just stick them out there. If you look at the kernel of this, then it's basically asking the question, what's the simultaneous solution of x congruent to 1 with respect to all the moduli? And by the extended Chinese remainder theorem, you just get 1, which shows you that it's a bijection. And then you can check the homomorphism property, and much like I did last time. So anyway, of course that applies to the Euler phi function to give us this. And great. So here's some actual examples. Finally. So if you wanted to find how many units there are in 200, what you could do is you find the prime factorization of 200, which is 5 squared times 2 cubed, right? Those are relatively prime, so it's isomorphic to that. And then remember, this is, oh, yeah, now I've forgotten some fine print. Thank you, Gauss. Gauss actually showed us that, now you already know this, U2 is the stupid group. I mean, U2 is a stupid group, right? But, sorry, U4, I mean, before the sunglasses, pretty good. After the sunglasses, eh. U4 is isomorphic to Z2. Hey, we had it right here. Hey, it's right there, 1, 3. And then this is not as obvious, I suppose, but the group of units 2 to the n is isomorphic to Z2 cross Zn minus 2. You have seen this in action with like 8. U8 was the Klein 4 group, right? And that would be Z2 cross Z3 minus 2 is 1. So like U8 is Z2 cross Z2. But fun fact, U16 is Z2 cross Z4. Up to isomorphism, of course. And this is more generally true. The group of units of size p to the n is isomorphic to the cyclic group of order p to the n minus p to the n minus 1 for any odd prime power. So with these in hand, you've got even prime powers, you've got odd prime powers. Admittedly, I haven't proved either of these things, and those are maybe not that easy to prove. I did have this name in the credits. Might worry you a little bit. This is one of those things in his, I can't say it, disquisitions, or I don't know. Anyway, his discussions about arithmetic. Anyway, so with these in hand, then I can apply those down here. Like, so the group of units of 5 squared times 2 cubed is isomorphic to the direct product of this and that. But by this guy right here, this is just Z20. And the U2 cubed, well, that's the Klein 4 group. We've actually seen that explicitly in here already. We don't need Gauss for that. We already know that. What's the group of units of 405 look like? Well, that's 5 times 3 to the 4th, obviously. And, I mean, not really. I forget. It's 5 times 81, right? Okay. And so that's U5 across the group of units of 3 to the 4th. That's a cyclic group of order z to the 81 minus 27. So apparently, the group of units mod 405 looks like Z4 cross Z54. It's not cyclic, right? Because Z4 and Z54 are not Ow, that hurts. Ow. Why'd I do that? I still gotta write power series on this board for the next hour. Grief. Shake it out. Shake it out. We should make a song about that. Let's see here. So this 4 and 54, of course, are not relatively prime, which means that that's not cyclic. You know? You can't reduce that to Z, like Z4 cross Z5, right? This is isomorphic to what? Z20. Because these are relatively prime, right? When can we reduce the direct product of cyclic groups to a isomorphic cyclic group of the same order? Is when the orders of the groups being producted are relatively prime. That goes both ways. For abelian, finite abelian groups. Here's 195. This works out to, in fact, Z4 cross Z2 cross Z12. I don't know. I think once you get started on this, it's just fun. I mean, it's pretty straightforward. If I asked you to find what the group of units is up to isomorphism of, say, like Z1000, you could do it. It wouldn't be a big deal, right? With this. But there's something else interesting. This has applications to classifying automorphisms of Zn. See, because we have proved that the automorphisms of Zn are isomorphic to the group of units of Zn. See, so if I want to find out how many automorphisms of Z100 have order k, that's kind of a daunting question. But on the other hand, if I want to figure out how many elements of U100 have order k, that's a fairly straightforward question because I know how to break U100 into things that I can understand. So U100 is isomorphic to Z2 cross Z20. How many elements of order, how many elements of order, what did I pick in here? 4. Elements of order 4 in there. Yeah. Oh, okay. Elements of order 4 in here, well, there you've got either element of order 1 or element of order 2, right? So to get the least common multiple of the pair that you're making from here to have order 4, I guess you got to have the order of B before, right? And you can either have the order of B before and this be either 1 or 0. So how many elements of order 4 are there in Z20? There's 2, right? Because phi4 is 2. Yeah. But there's 2 elements of order 4 here, but there are 2 choices here that will give me a least common multiple of AB being 4. So I get 2 times 2, I get 4 total choices, 4 elements of order 4 in Z2 cross Z20. Not that it matters, but here they are. All right. So therefore, by this isomorphism, and the fact that isomorphism preserves orders, right? it follows that there exist 4 automorphisms of Z100, which have order 4. Now, if you're just asked to find how many automorphisms of particular order there are for, Zn, I don't think that's a very easy question without this theory, right? I mean, maybe it is, I don't know. Doesn't seem easy to me. Galilean has a even greedier example. I have it if you want to look at it. Now, we need this for the last part of my talk, which is on encryption. Don't worry, I will not steal much of your thunder. I just want to, I'll do a bad job on the next 10 minutes. So anybody who's talking about encryption in another course can still talk about it, okay? I won't test on encryption, so it doesn't really count, okay? Although I might test on the calculations in the encryption, so it's not an entirely honest statement. But you've gotten used to that with me. So this is Euler's theorem. It says that x to the phi of k is congruent, is equal to 1 mod k. I guess I should say congruent to 1 mod k there. So we've talked about this previously. That is actually really important for the RSA encryption I'm about to describe. So RSA encryption is how we send email and other things without worrying about people snooping in our stuff, for the most part. I mean, RSA encryption is built into all kinds of stuff. So it's been around since a little bit before I was born, 1976. Oh, wait a minute, that's when I was born, 78, right there. So apparently there's some British dude, oh, there he is, Clifford Cox. Also invented it in the 70s some point. But the R is for Rivest and Shamir and Edelman. I'm probably mispronouncing those, but it's okay. They're not here. And anyway, so here's the basic idea. Because it seems like magic that you can just send data and also the key for how to interpret the data, how to encrypt the data, and yet it's secure. Like, that seems very weird, right? Like, the more classical notion of encryption is you send some coded message, right? But then you send the coded key also through some other method, like secretly. So then when you put them together, then you can, like, we've all seen various adventure stories based on this basic idea, right? They can't unlock the map until they find the whatever to look at it through and so forth. I don't know. You know what I'm talking about. So here's the RSA algorithm roughly. Number 1, you choose a pair of large primes, P1 and P2. You take their product and you call it n. This is huge in real applications. Number 2, you calculate this n and you choose an encryption exponent, e, such that the greatest common divisor of e and the Euler phi function of n is 1. So you need that the encryption exponent is relatively prime to the Euler phi function of n. Indeed, you could. That's right. So the Euler phi function of n, given what we were just talking about, is equal to P1 minus 1 times P2 minus 1. Assuming that, of course, P1 and P2 are relatively prime. But come on. P1 is not equal to P2, okay? Did I say distinct? Oh, shame on me. Anyway, you publish in the Journal of Encryption. No, to your friends, whoever you're talking to. E and n, the encryption exponent, and the product of the, you don't give them P1 and P2, you give them n, all right? The whole stupid thing with its hundreds of digits. And then anyone can send you an encryption message subject to the commonly held conventions, which I will describe now. And this is a lie. The actual RSA encryption is a little bit more, there's some other things built into it than just this. This is the naive toy model of it, of course, but how you do it is your friend takes a message and he uses simple transcription to translate it into a coded number. For example, you might take the word cast and you can transcribe that to 03011920. I need to wear my glasses. So there I'm using A is 1, B is 2, Z is 26, and I'm taking 4 letters at a time. So cast becomes this 8-digit number, If you had, cast members, then you'd need more, right? You need the one for the cast, you need another 8-digit number for the start of members, then you need another one for the end of it. You need some kind of system to realize that they're linked together. I'm not sure exactly how. That's the part I don't know. This is roughly it, though. You understand we can use the alphabet code to change any word into an integer through a pretty systematic method, right? That doesn't have to be secret either. This is just simple, straight transcription. Although this would suffice for coding when you're in elementary school, right? So then, all right. So let us agree that m denotes the message, all right? And m is going to be some natural number, and we also need it to be such that it's less than n. But that's okay, because our relatively prime, I mean, our n is huge, so it's not an issue.
And also we break that into blocks if the message is too large.
Right. That's more of the details I'm not getting into, but yes. Your friend takes n and e, you publish, and he runs the message through the encryption map, m to the e, which scrambles the message to the encrypted message, f of m, which again is m to the e. And then they communicate that to you without hiding it, right? Anybody can intercept it mid-transmit, doesn't matter. Even if your interceptor knows both n and the encryption exponent, doesn't matter.
And this is m to the e mod n specifically, right?
N to the what?
M to the e mod n.
M to the e mod n.
Because otherwise, it wouldn't be discrete logarithm, it'd just be regular logarithm computer calculated, right?
Yeah, I mean, I think this is being done mod n, right? Yeah. Now, but since you know P1 and P2, mind you, these are not public. The decomposition of n into the product of primes is not known. That's not public. But you know what P1 and P2 are. You can take that and you can figure out what phi n is. See, finding the Euler phi function of the national debt is not something that you can do easily. Because telling how many units there are in a very large prime is really, really difficult. But it's not really difficult if you know what the thing is. And since you know what it is, and you know that the encryption, you know that ED, well, this is D is the decryption exponent. So DE is equal to 1. And then you do the decryption exponent on your message. Then by the Euler's theorem, this is just 1 again. And there you go, back your message, mod n. And so, in other words, you can take the encrypted message and run it through the decryption exponent, and then you get m. And other people who don't know the breakdown of n can't do this. So the only thing that's really keeping your message safe is the fact that other people can't factor the product of primes that you gave them. The whole method is based on the idea that I give you whatever number and you can't break it into a product of primes. Again, it's built from 2 large primes. So I do this to my children in the summer. They say, can I go outside? And I say, sure, just factor this number. And what I usually do is take like 23 and 29 and multiply them. Something like that. It takes them a while. They just start long dividing. Eventually they get it. Here's an actual example where I use 13 and 17 as a toy example. I encrypt it. When I encrypt it, I get a number, and then I decrypt it and get back to the message again. You can look at it, but we're out of time, I think, so I'll shut up.